And Marino Gran, who I'm very honored to welcome here as the first speaker, knows this already. And in fact, you may not see him from the video broadcast, but he's already standing far from me. But I'm very glad to check time, and let me start on time. I give him the floor, physically so. Thank you.
So good morning, everyone. And first of all, a very big thank you to the organizers, all the organizing committee, who bravely organized this conference, which is very important for our community. And I think it's so good to see face by face again that it's a kind of celebration, this CT 2021. Thank you very much. I would like also to thank the scientific committee, Matthias Meni, first of all, and all the members of the scientific committee for giving me the opportunity to speak at this conference, CT 2021. And thank you all for being here. Also to all the participants online that I cannot see, but I know that we share the same passion for category theory. So thank you for being with us. So this work that I'm going to present today is about pre-torsion theories. And I would like to switch to the next. Is it possible to use this? Okay, thank you. So in the first part of the talk, I will try to explain the motivation and how one goes from the classical notion of torsion theory, say in an abelian category, to this notion of pre-torsion theories, and prove some simple properties of pre-torsion theories that essentially were proved in collaboration with Alberto Facchini and Carmelo Finocchiaro. Then we shall examine one specific example of pre-torsion theory, in the category of internal preorders, and we shall try to explain the universal property of the stable category of this in this specific example. And so in the last part, we'll present some results in collaboration with Aline Michel on a pre-torsion theory that we have found in the category of preordered groups. So let me begin by recalling first the definition of a torsion theory in an abelian category. So it goes back probably to Dixon, I think, at least in the abelian context. A pair tau f of full replete subcategories in an abelian category is a torsion theory if two properties are satisfied. So first of all, the only morphism from an object in the subcategory tau to an object in the torsion-free subcategory F is the zero morphism. And the second property is to have, for any object C in the abelian category, a short exact sequence where the kernel belongs to the torsion subcategory and the quotient belongs to the torsion-free subcategory. Of course, the terminology, torsion subcategory, torsion-free subcategory, comes from the classical case when C is the category of abelian groups, tau is the category of torsion abelian groups, and F the category of torsion-free abelian groups. So in this specific example, which is the example, one has that given an abelian group A, one takes the elements of finite order, they form a subgroup T of A, and by making the quotient, you get the universal torsion-free abelian group associated with A. So in the last years, there has been a lot of work on non-abelian torsion theories. Already in the paper by Cassidy-Berkeley, which is the reference for factorization systems, they work at some point in a context where monomorphisms are characterized by the fact that the kernel is zero. And so they speak of quasi-additive categories. And later on, in the last, say, 15 years, there has been a lot of work to try to explore the properties of torsion theories in pointed categories, which are no longer additive. For instance, groups, topological groups, we shall see co-commutative Hopf algebras and other situations. I don't want you to read all this list of papers, just to indicate that there's a lot of work going on this. And here I'm just speaking of the torsion theories in a pointed category, when there is a zero object. The point is exactly that the same definition that was given by Dixon in the case of an abelian category still makes sense in any pointed category. So you can still take two subcategories tau and f, ask that the objects in the two subcategories are, so to say, orthogonal, and you ask the existence of a short exact sequence associated with any object in your category. So some of the examples that were considered recently, of course, in the semi-abelian context of commutative rings, not necessarily with unit, was the torsion theory whose torsion part is the category of nilpotent commutative rings, and the torsion-free part is the category of reduced commutative rings. And here, given a ring R, by taking the nil radical, you get the torsion object associated with it, and by taking the quotient, you are making your ring reduced in a universal way. In a completely different context, if you take topological groups, you can consider indiscrete groups and Hausdorff groups in the category of topological groups. And here, I shall try to use this thing. So given a group G, you close the trivial subgroup of your topological group, and by taking the quotient, you get the T0 reflection, which is also the T2 reflection in the case of topological groups. A more recent example that we observed in collaboration with Gabriel Cajot and Jos Verkooys is a torsion theory in the category of co-commutative Hopf algebras. So when K is an algebraically closed field of characteristic 0. So here, the Milnor-Moore theorem says that any co-commutative Hopf algebra is canonically isomorphic to a semi-direct product of a primitive algebra and group Hopf algebra. Hopf algebra is called this semi-direct product smash product. And here, the kernel, so of the canonical short exact sequence, is the universal enveloping algebra of the Lie algebra of primitive elements of H. So what I've written here, LH, are the elements X in H, such that the co-multiplication of an element X is 1 tensor X plus X tensor 1. And K of GH is the group of algebra generated by the group elements. So in this gives the canonical short exact sequence that in this case is also split, and essentially says that one could say Lie algebras and groups form a torsion theory in the category of co-commutative Hopf algebras. Now, the point of this talk is to go beyond the pointed case. So the first very simple observation is that whenever you have a torsion theory, the intersection of the torsion and the torsion-free subcategory is reduced to the zero object of your category. This follows immediately from the fact that if X is assumed to be in tau and in F, this morphism, the identity should factor through 0, and then X isn't necessarily isomorphic to 0. Now, the idea of a Pretorsion theory is simply to replace 0 with the intersection of tau and F. So Z, the subcategory of trivial objects, will be the subcategory generating an ideal of Z trivial morphism. So we replace 0 morphism with Z trivial morphism. What is a Z trivial morphism? It's what you would expect, namely that a morphism F is Z trivial if it factors to an object Z in the subcategory of trivial objects. Now, we have two axioms in the definition of torsion theory. So we have to express the existence of the short Z-exact sequence associated with any object in your category. And so for this, we need the notion of short Z-exact sequence. And this is not new, it is actually the notion of kernel relative to an ideal of morphism. So if you have a morphism F from X to Y, then K will be the Z kernel of F if on the one hand, the composite of K with F is trivial. So think of the classical case, it should be 0. And moreover, we have the expected property that whenever there is an L, such that FL is a Z trivial morphism, then there exists a unique factorization towards the Z kernel. So it's exactly the same situation as in the pointed case, but we are allowing a whole category of trivial objects. Of course, the notion of Z co-kernel is defined dually, and it's immediate to check that a Z kernel is a mono and a Z co-kernel is an epi. So the sequence of two consecutive arrows K and F will be called short Z exact if K is the Z kernel of F and F is the Z co-kernel of K. Again, taking Z equal to the trivial subcategory with a zero object, one gets back the notion of short exact sequence. So we are now ready to give the definition of pretorsion theory. So if you have a category C, and tau and F are two full replete subcategories of C, replete means closed under isomorphism, then it is a pretorsion theory if any map from a torsion object to a torsion-free object factors through a trivial object. So it is Z-trivial. And you can find for any object C in C, a short Z-exact sequence where the Z kernel belongs to tau and the Z co-kernel belongs to the torsion-free subcategory. So it's quite simple to show that any torsion-free subcategory for a pretorsion theory is reflective, and any torsion subcategory is co-reflective, as in the classical case for torsion theories. And just to see how it works, so if you take any object C, you have the canonical short Z exact sequence associated with the C. You want to show that eta C is the unit of the adjunction. So for that, you just consider any morphism F to a torsion-free subcategory, to an object F1 in the torsion-free subcategory F, and you remark that T of C belongs to the torsion subcategory, F1 belongs to the torsion-free subcategory, and this implies, by the universal property of the Z co-kernel, that F factors through eta C, giving then the universal property of the unit of the adjunction. One interesting point is that if you have an object in the category C, it will belong to the torsion subcategory precisely when all morphisms from X to any torsion-free object is trivial. So the point, which is simple to check, is that any two of the three subcategories tau, F, and Z determine the third one. Of course, if you have tau and F, Z is just the intersection of tau and F. But also if you know the torsion subcategory and the subcategory Z of trivial objects, then you can determine F and vice versa. Just to see a simple example of a pretorsion theory, you take a set partially ordered, so 1, 2, n is a chain, and then the two subsets tau and F of X form a pretorsion theory if and only if, first of all, the union of the objects in tau and the objects in F give every object in X. The first object, 1, belongs to the torsion subcategory, the last object to the torsion-free subcategory. And the property here says that if you have two consecutive objects, I and I plus 1, such that the first one is in tau and the second one is in F, then either the first is also in F or the second one is also in tau. So one of the two has to be in Z, in the trivial subcategory. So some properties of pretorsion theories. So first of all, the three categories tau, F, and Z are all closed in C under retracts. They also close under Z extensions. This is something that is well known in the case of abelian categories. The fact that the torsion subcategories and the torsion-free subcategories are closed under extensions. Here we can prove that the same property for pretorsion theories. So if S1 and S2 are torsion, then X is torsion, provided these two consecutive arrows form short Z exact sequence. So we shall say that reflective subcategory F is Z normal epireflective if, first of all, the inclusion of the torsion-free subcategory F has a left adjoint, of course, and then each A component of the unit of the adjunction, eta A, from A to UF of A, is a Z cokernel. So in particular, this tells us that the subcategory F is epireflective. Only epireflective in this case. So what we observed with Alberto Facchini and Carmelo Finocchiaro is that given a category C and Z a full subcategory which is closed under retracts, then the following conditions are equivalent. F is the torsion-free subcategory of a pretorsion theory tau F in C, where of course the subcategory of trivial objects is tau intersecting with F. Or three properties are satisfied. F is epireflective in C. For each component eta A of the unit of the adjunction, one has a Z kernel. And moreover, the canonical map from T of T of A into T of A is an isomorphism. So one direction of this proposition is very simple. So if you have a pretorsion theory, we have already seen that it is Z normal epireflective. We have proved it. Now, the fact that it has a Z kernel corresponds to the fact that you have this short Z exact sequence associated with A. And this fact that this is an isomorphism simply follows from the fact that the Z kernel of a trivial map is always an iso. What is interesting is the other implication. So assume that you have an epireflective subcategory that satisfies these three properties. So in this case, you define tau, what will be the torsion subcategory, as those objects in C such that eta A is Z trivial for each A. Sorry, those A such that eta A is Z trivial. So by definition, Z is contained in tau, because if A is in Z, then the morphism starting from an object in Z is trivial. Then the point is to show that Z is the same thing as the intersection of tau and F. And for that, you consider first, we have noticed that Z is contained in tau. Now we prove that Z is contained in F. And for that, we consider Z in Z. The Z kernel Tz of the reflection exists by the assumption B and is Z trivial, because Z is a trivial object. So this implies that its cokernel is an isomorphism and gives us the fact that Z is isomorphic to UF of Z, where U is the inclusion and F is the reflection. So first, we have this inclusion, the Z is contained in tau intersecting with F. On the other hand, to see the other inclusion, take any A in the intersection of tau and F, then eta A is an isomorphism because A is in F, so when you reflect it, you just get an iso. On the other hand, eta A should be trivial because it belongs to tau, so by definition of tau. So the conclusion here is that your A is a retract of Z, And then it belongs to Z, because by assumption, Z was assumed to be closed under retracts. And so you have the coincidence of Z with the intersection of tau and F. So this is the main point, and then one checks that one has a pretorsion theory. So another small observation is that if you have a torsion theory in abelian context, then the torsion subcategory is stable under quotients, and the torsion free is always stable under subobjects. We do not have this property in full generality. We have something close to it when the subcategory Z is consists of projective objects with respect to epimorphism. So in this situation, we can prove that tau is always stable under extremal quotients and F is stable under subobjects. The main obstruction here is just the fact that epi plus mono is no longer iso in this very general context. So just a few remarks to conclude this first part of the talk is that the notion of a category equipped with an ideal of morphism is due to Charles Ehresmann in '64. Then there is a connection, by the way, between Louvain-la-Neuve and Genova. So La Vendôme also studied category with this ideal of morphism, and Marco Grandis did a huge work in the categorical foundations in homological and homotopical algebra. Here I'm mentioning a paper of '92 in the Cahiers, but actually there's a whole list of articles and books about this approach of a category with an ideal of morphism. Now, more recently, it has been used by Zurab Janelidze and Aldo Sin and me to compare exactness properties in categorical algebra that occur in pointed categories and in non-pointed categories. And also Diana Rodello, Olivier Gaha, Florence Sterck, and Basileios Aravantinos Sotiropoulos investigate various aspects of this approach. Now, the notion of pretorsion theory itself was introduced by Facchini e Finocchiaro very recently. It's a paper that appeared in 2020, and it was in the appendix, they give this very natural and simple definition. And then we have worked together to investigate some of the properties of these pretorsion theories in general categories. And there are very close notions, which are due to Marco Grandis, George Janelidze, and Laszlo Marchi in a paper in 2013. There was an invited talk of Sandra Mantovani at a workshop in Louvain-la-Neuve in 2014, where she was also studying torsion theories in non-pointed context in a situation which is very close to ours. One difference is that the category of trivial object is not required in our approach to be at the same time reflective and co-reflective. That's one of the differences. And there is a recent paper by Marco Grandis and George Janelidze on torsion theories in non-pointed context, which is also very close to ours. So perhaps it's a good point to make a small break. I'll drink some water. If you have questions, please do.
There is a question.
Ah, yes, yes, please. Yes.
Can you repeat the question? So everybody.
Yes. So the question is, what are the examples? Right. Yes, and this is the second part of the talk, basically. So I will present now an example which is important for us, and there are several ones that I will not be able to present today, but are other already in papers around in the context of quandles, topological spaces. But I will mention this at the end. So today I will concentrate on one example because I find it particularly interesting. Actually, two examples. And then I will give references to other examples which are, I think, quite relevant. So we have an exact category. We shall be working in a category C, which is regular, and such that all equivalence relations are effective. So I guess this is a well-established notion. So we assume the factorization regular epi followed by a monomorphism for any morphism in the category. So we shall call I the image of F. We also assume that regular epimorphisms are stable under pullback. So the first two properties, under the assumption the category is finitely complete, mean that the category is regular. And moreover, I assume that equivalence relations are effective. So any equivalence relation occurs as a kernel pair of some arrow in the category. So we consider therein the category of internal preorders in the exact category C. So these are reflexive and transitive relations, which will be represented in this way. So rho has two jointly monomorphic arrows, R1 and R2, to A, that I will briefly denote by A rho. And morphisms will be pairs of arrows, I don't know, yes, pairs of arrows F and F bar, such that these diagrams commute. I don't know if this is visible, this lower part. So this means that F of rho is contained in sigma. It's, well. Probably here it's not so important, but we are expressing internally the fact that F is a monotone map. Now, a pretorsion theory, thanks. It should be fine, yes, I think. Yes, now it's fine. So, So, in the category of internal preorders in C, we have the subcategory of partial orders, with the property that the intersection of rho with the opposite of the relation rho is the trivial, the discrete relation on A. So this is just the fact that we're expressing the fact that if X is less or equal than Y and Y is less or equal than X, then X equals Y. So we shall write partial order C for the category of partial orders in C. And we shall call, we know that an equivalence relation is simply a preorder such that the opposite relation of rho is rho itself, so it's symmetric. And so we have the category of internal equivalence relations in any finitely complete category C. We shall actually be interested in particular in the case when C is an exact category. So quite obviously, the intersection of internal equivalence relations and partial orders is the category of discrete equivalence relations in C. This is just the fact that an equivalence relation in set, for instance, and which is also a partial order, is the equality relation. And this is an example of a torsion theory. So if you take equivalence relations in C and partial orders in C, this gives you a pretorsion theory in the category of internal preorders in C. So how do we prove that? We consider the intersection of rho with the opposite relation rho op, and we write pi for the canonical quotient. So we go from A to the quotient of A by tilde rho. This quotient exists because we are in an exact category. And then, oops, the discussion hides the diagram actually, but yes, thank you. So we get this diagram starting from rho, which is an internal preorder. We have defined tilde rho, which is the intersection of rho with its opposite relation. It is, of course, an internal preorder, but it is by construction symmetric. Then we take the quotient of A by tilde rho, and we take the factorization, regular epi, jointly monic pairs of these two maps. It turns out that this quotient is actually a partial order. So we have here what can be checked to be a short Z exact sequence with the kernel in equivalence relations and the quotient in partial preorders in C. To see that any morphism from an equivalence relation to a partial order is trivial, we just have to compute f of rho and show that this image is trivial. And so here it's simple because rho is just the intersection of rho with its opposite, because we are assuming that rho is an equivalence relation. Sigma, on the other hand, is a partial order. So by simple calculation, we find here sigma intersection with the opposite of sigma. And since this is a partial preorder, this is just delta B. So we have proved that any morphism from an equivalence relation to a partial order is a trivial morphism. So we have proved that our pair formed by the equivalence relations in C and by partial orders in C is a pretorsion theory. Now it turns out, when C is exact, that the reflector F from preorders to partial orders in C, which associates with the internal preorder rho, pi of rho, which is the image of these two maps, so the regular epi jointly monic factorization of these two maps. So this reflector has stable units in the sense of Cassidy-Berkeley. So very simply, this means that it preserves not all pullbacks, but all pullbacks where the bottom right object belongs to the subcategory. In our case, to the subcategory of internal partial orders in C. So it gives then an admissible Galois structure in the sense of categorical Galois theory of George Anelidze. And this, in the case when C equals sets, actually we can find a monotone light factorization system of any arrow in the category of preorder sets, where any map can be factorized as stably invertible map. So E will be a morphism which is inverted by the reflector, and it is stably so. And the induced morphism M, induced by the quotient here, is actually a covering in the sense of categorical Galois theory. The coverings relative to this admissible adjunction are precisely the morphism with the Z kernel that belongs to the subcategory of partially ordered sets. So in the case C equals sets, we know that preordered sets is a category which is isomorphic to the category of Alexandrov discrete spaces, which are the topological spaces with the property that the intersection of any family of open subsets is open. So the isomorphism here associated with preordered sets, the topological space is A tau rho, where a subset X belongs to the topology if and only if it has the property that if X belongs to X and the pair AX is in the relation, then A belongs to X as well. So by looking at the pretorsion theory here in the category of preordered sets via these isomorphisms, we obtain pretorsion theory in the category of Alexandrov discrete topological spaces. So part Alex is simply the category of Alexandrov discrete spaces. So it is the category of Alexandrov discrete spaces with a partition topology. So a basis of the topology is a partition of X. And the torsion free, so to say, subcategory is given by the Alexandrov discrete spaces, which are T0. So this adjunction between partially ordered sets and preordered sets gives the adjunction between Alexandrov discrete spaces and the T0 one. So we have the T0 reflection. And here the Galois coverings relative to this adjunction, which is admissible, as I said, are precisely described as the morphism in Alexandrov discrete spaces, such that any fiber of any fiber is T0. This can also be deduced by another general result of Georgian and Litz concerning T0 reflections in general. What we add here is that we have a class E prime, which is formed by the regular epis such that the fibers have the indiscrete topology. And so we get another monotone light factorization system in the terminology of Carbonija and Litz-Kelly-Paré, where E prime, again, I recall, are the stably inverted morphisms of C, and M star are the coverings for the Galois theory. I don't know if there are questions at this point. Okay. So I will try to explain how we interpret nice construction due to Alberto Facchini and Carmelo Finocchiaro, who associate with the category of preorder sets what they call a stable category. So this construction basically wants to associate with this pretorsion theory that I have already just explained, a torsion theory, even if it is not explicitly said in their paper. So the idea is to make the category of non-empty preorder sets pointed. So they want every trivial preorder to become the zero object, and any z-trivial morphisms to become a zero morphism in the quotient. And so with Francis Borseux and Federico Campanini, we have studied this construction from a more categorical perspective. And actually, we have a definition that makes sense when C is any pretopos and clarifies also the universal property of this stable category. So first, recall that a pretopos, since I'm always assuming that the category has finite limits and is exact, is a category which is also extensive in the sense that in any commutative diagram like this one, where S1 and S2 are the coproduct injection, the top row is a sum if and only if the two squares are pullbacks. Note that when C is a pretopos, the category of preorders in C is not even regular, so it is certainly not a pretopos. In order to define our stable category, we want to speak of complemented subobjects. So we know what a complemented subobject is in a pretopos. So these are the subobjects A and AC, such that the intersection is the initial object and the supremum is the whole object B. And now the idea of the stable category is to identify two morphisms in the category of internal preorders in C if they coincide on a complemented subobject and are both trivial on its complement. So how one can express this categorically? So we need to know what a complemented subobject is in preord C. And this is not difficult to characterize. These are the complemented subobjects at the base level in the category C, which is assumed to be a pretopos, with the additional property that on the one hand, the restriction of the preorder on sigma on A is precisely rho, and together with the restriction of sigma on its complement, because we are assuming that alpha is complemented, rho and the complement of rho gives sigma. So sigma is the coproduct actually of rho and the complement and a rho complement. So these are the complemented subobjects in preord C. And so we first build the category of partial morphisms in preord C, where the objects are, of course, internal preorders. Morphisms are partial morphisms, so we have a complemented subobject alpha and morphisms in the category of preord C. So we shall represent alpha f with this parenthesis to say this is a partial morphism from A rho to B sigma. And the composition, as we know, is given by pullback. So if you have two composable morphisms, alpha f and beta g, then to compose them, you simply pull back f along beta here, and you get the definition of your composition in the category of partial morphism in period C. So the functor that we obtain this way is a functor from period C to partial periods, sending our f to, of course, this diagram, where we have chosen as complementary subobject the identity on the period A rho. Now, the stable category of period C is a suitable quotient of the category of partial morphism in period C. So the idea is simple. So we want to identify alpha 1 F1 with alpha 2 and F2 when we can find a congruence diagram of this type. So this means that there exists a complemented subobject A0 both in A1. So A0C is the complement in A1 and in A2. So A0 to C is the complement in A2, such that F1 coincides with F2 on this subobject. And on the other hand, if we compose with the inclusion of the complement, we get a trivial morphism from A01C to B and from A02C to B. So we can find a subobject on which the two morphisms coincide, and they are trivial outside. So this is just the same diagram, but I have made more explicit the conditions of the diagram. So finally, we can find by composing this quotient. So first of all, by using this identification, we get an equivalence relation which is also compatible with composition in the category of partial morphisms in period C. So we can go to the quotient and have this functor pi. And by pre-composing with the inclusion of period C into partial morphism in period C, we get a functor sigma from the category of periods in C to the stable category. And now we can prove some properties of this stable category. First of all, it is a pointed category with zero object, the image of the initial object of the pre-topos the zero object of period C, 0, which is initial. I mean, 0 is initial and sigma is 0 becomes a zero object in the stable category. On the other hand, a morphism F is the trivial if and only if sigma of F is a zero morphism, exactly as in the presentation of Facchini-Finocchiaro. And this functor sigma preserves finite coproducts and monomorphism. This is important to prove the universal property of this stable category. So this stable category has the following characteristic, actually. First of all, the functor sigma that we have just defined is a torsion theory functor, by which I mean a functor that sends each torsion object of the domain category into a torsion object of the codomain, and each object of the torsion-free subcategory into the torsion-free subcategory. It transforms the pre-torsion theory into a torsion theory in the quotient. And the canonical short exact sequence that I mentioned before becomes a true short exact sequence in the stable category. So, in other words, the universal property of this functor from period C to the stable category is of being universal among all finite coproduct preserving torsion theory functors from period C to another category X, where we have fixed a torsion theory. So this is the best torsion theory that one can associate with the pre-torsion theory in period C. Furthermore, the induced functor G bar is such that G bar sigma, is such that it preserves finite coproducts. So G bar itself is a torsion theory factor, and it preserves finite coproducts. Of course, this preservation of the finite coproducts is related to the fact that we have complementary subobjects, and so morphisms are determined essentially by how they behave on the two complements, on the two subobjects, one and its complement. So in this sense, the stable category provides a universal torsion theory associated with the given pretorsion theory, equivalency, and partial orders in C. I think I have to go a bit quicker now. So in the category of pre-order groups, we have a similar phenomenon, even though groups, of course, has nothing to do with a pretopos. And what we have now is a pretorsion theory. But before presenting the pretorsion theory, let me just recall that a pre-order group is a group endowed with a pre-order relation that is compatible with the group operation plus. So if A is less or equal than C and B is less or equal than D, then A plus B is less or equal than C plus D. So a morphism from G to H in the category of pre-order groups is a monotone group homomorphism. Now, let me underline one fact. Pre-order groups are not the internal pre-orders in groups. And the reason is that the opposite is not a monotone function. So we only require compatibility between addition and the order relation. So any pre-order group has a positive cone that is usually denoted. So if G is a group, PG is the positive cone. That is a submonoid of G, which is stable under conjugation. And this leads to an alternative presentation of pre-order groups, which is well known. So the objects here are pairs G, PG, where G is a group, PG is a submonoid of G, which is stable under conjugation. And the morphisms are just pairs of morphisms. I mean, you can see it as a group homomorphism F that restricts to the positive cones. So there is a nice result by Maria Manuel Clementino, Nelson Martins Ferreira, and Andrea Montoli, quite recent, that shows that the category pre-order groups is normal in the sense of Zura-Giabelizze. So this means that this is regular, pointed, and every regular epi, every co-equalizer is actually a co-kernel. So it's a nice category, even though it is not as nice as topological groups, as mentioned in the paper by Clementino, Martins Ferreira, and Montoli. It also has a very important property for Galois theory, in the sense that normal epis are effective for descent. So we can do Galois theory in this category quite naturally. So the category of pre-order groups contains two full subcategories that will be interesting for us to get at pretorsion theory. So the partially ordered groups, which in terms of the positive cone are those pre-order groups such that x plus y equals 0 always implies that x equals 0 and y equals 0. And on the other hand, we have what are called the protomodular pre-order groups. I'm not going to go into the detail of that, but it is essentially a notion that allows one to have some objects that behave more like groups in categories which are not protomodular. So things, for instance, of groups in monoids. So they characterize in this paper the protomodular objects as the pre-order groups such that the positive cone is a group. So I see I have 2 minutes. So I will skip the proof that will be on the slides. So the protomodular pre-order groups and the partially ordered groups form a pretorsion series. The class of trivial object Z actually here is just given by the pre-order groups where the positive cone is 0. Well, in order to obtain the canonical short Z exact sequence, one takes NG to be the set of elements such that both N and its opposite belongs to the positive cone. This is a normal subgroup of G. You take the quotient, you factorize, and you get the canonical short Z exact sequence associated with your pre-order group GPG. Sorry, I have to skip this. So to conclude, this category of partially ordered groups is reflective in pre-ordered groups. The torsion subcategory, as usual, is co-reflective. So the protomodular objects are actually both co-reflective and reflective in the category of pre-ordered groups, as we observe. And the main result in this paper in Algebra Universalis with Michel concerns actually the adjunction between these two categories, so partially ordered groups and pre-ordered groups. This reflector F has stable units again. So we have a Galois structure. We can characterize the coverings therein, which are precisely the morphism FF bar in pre-ordered groups, such that the kernel belongs to partially ordered groups. And we also have a monotone light factorization system in the sense of Carboni, Gianellizze, Kelly-Paré, where the class of stably invertible morphism E prime is given by the normal epis, such that the kernel is a group, where when I say that the kernel is a group, I mean that its kernel is given by G, which is the positive cone of G itself. So here we have the identity as inclusion of the positive cone in G. Probably have to conclude. So these are some remarks concerning the proof, but let me just say a few words. The description of the coverings that we have obtained is similar to the ones in a paper by Gianellizze Marchi-Tolen of locally semi-simple coverings. It would be nice to extend the results that we have for pre-orders in a pretopos to cat C, where C is a pretopos. A first step in this direction has been made by João Charest, that has found a pretorsion theory in cat. And to, in some sense, answer Jirka's question, pretorsion theories appear in very many other contexts. I mentioned internal categories, internal pre-orders, pre-order groups, V groups for V suitable quantiles, topological spaces. We have seen only the example of Alexandrov discrete spaces, quandles, and sometimes they induce semi-localization or reflection with stable units. And so it would be nice to have a general criterion to establish when we get monotone light factorization systems out of these pretorsion theories. We have such a result in the case of torsion theories in some suitable non-abelian categories like semi-abelian categories. I think I stop here. Thank you very much.
Thank you. We have time for 2 quick questions, if any. Is there any question online? Raise your hands, please. Steve, we are going to open your audio. Okay.
Hello. Thank you, Marino. A beautiful talk. If I understood correctly, your construction of the stable category, it looked like what you're doing was universally inverting the complemented monos. Does that sound right to you?
I missed the beginning of the question. Sorry.
Your construction of the stable category.
Yes.
Where you first formed the partial maps and then you identified some of these. This looks like the construction of construction due to Benabou with respect to the complemented.
Well, thank you, Steve. I don't know if of the relationship with the construction of Benabou, but please send me the reference. I will have a look at it.
There is another question from Paul Taylor. We're just going to open your mic.
Well, it's journal.
Hello. Stephen, I think I'm unmuted now. Thanks for a nice talk, and thanks to Pino and the organisers. Short exact sequences in abelian categories work and are just as general as the standard notion of kernel and co-kernel in category theory because of subtraction. But you've got rid of subtraction. So you have some more restricted notion of kernel and co-kernel than the standard one, which presumably means you have a more restricted notion of regular mono and regular epi. And I'm just wondering whether, following that line, you have something similar to, I'm not sure whether they're called weak factorization systems or model systems in homotopy theory. I wonder whether that's another connection that you could add into your theory.
Thank you, Paul. We don't so far have connections with weak factorization systems. The paper on, approach to torsion theories which are non-abelian, which takes this into account, is due to Jirka Rosicki and Walter Tolle. But they work still with the standard pointed context I was mentioned at the beginning. So what we should do, and we have not done yet, is to try to see how much of their work can be adapted, can be transposed from a torsion theory to a pretorsion theory. But this we have not done it yet. So I think the best paper making this connection with weak factorization system and torsion theories clear is the paper by Walter Tolle and Jirka Rosicki in Journal of Homotopy and Related Structures. But we need more work for that.
Thank you everyone for the question, and let's thank Marina again for the very nice talk. Thank you.